Today we will learn about band theory of solid, which is very important in solid state physics. Here, first we will learn about free electron gas model. The free electron gas model. Here, initially we will consider classical mechanics. Classical mechanics, which is explained by Maxwell-Boltzmann distribution. Here, how electrons or particles are distributed in different energy state. In this distribution, the factor is exponential minus (1 by kT). Exponential minus E by kT, which is the function of energy. This factor function of energy in Maxwell distribution. But in this, by using this distribution, we cannot explain all properties of free electron gas, because electrons are fermions and they are distributed in different energy state. That's why we will consider here will energy distribution function, and this is Fermi-Dirac distribution, which is explained by quantum mechanics. By this, we will explain most of the properties of free electron. Here, the distribution is Fermi-Dirac distribution, and the factor of energy is 1 by exponential E minus EF by kT. By using this distribution, we can explain all the properties, most of the properties of free electron. Now, on the basis of electrical properties, we know solid is classified. Solid are classified by metal, semiconductor, and insulator. Metal, semiconductors, and insulators. In metal, free electron can pass easily, but in semiconductor, electrons cannot pass. We have to apply temperature. By increasing temperature, the resistance will be decreases. That's that type. This type of solids can pass electricity in this semiconductor, that type electron can pass through this matter, through this solid. An insulator, there is a very big energy gap, that's why there is no free electron in the valence band which can easily go to the conduction band, which cannot go easily to the conduction band. So insulator cannot pass electricity. We will consider for this model only metal, because in metals there is huge free electrons in the valence band, but in semiconductor and insulator there is not much free electron. If we relate with this metal, so we will consider only metal for this model of free electron. Now we also know the term of Hall effect. Okay, in Hall effect, for this model, experimentally we get only negative coefficient. For this model we only get negative coefficient, but experimentally we get negative and positive both coefficient value. So if we consider free electron gas model, here we get negative coefficient, not positive. Now if we consider a box where is only electrons according to free electron gas model. At first I will write the model name, the free electron gas model. In this model, if we consider a box of electron where only is electron, and there is nothing, only there is electron. But if you consider a crystal, every electron attached with its neighbor atom, here atom, 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 atom in a periodic form. They are arranged in a periodically and in a good manner. This is the formation of crystal lattice. So here atoms and electrons are attracted or repulsion, attraction. There is attraction or repulsion in between electron and atom. That's why there is an electrostatic force like repulsive force or attractive force. So they are in equilibrium. So in free electron gas model, if we consider a potential energy, is Vx, is independent on x, That's why potential energy equals to Vx. Now if we draw a curve like this, if you consider here an atom, the potential being like this. If you consider here another atom, the potential being like this. And in a crystal there are lots of atoms, so the potentials will be like this. So this is X and this is Vx. Now if we consider only lattice, here and it is one-dimensional lattice, so the potential be like this, the potential be like this, the potential be like this, and this is gone. So this is potential side, and this is also potential side. And this is lowest point of potential, and this is maximum point of potential. Now mathematically it is very difficult to understand this potential, so we have to simplify. So now if we consider here like this, like square potential, so this is zero potential, this point is V0, there is some potential. Now if this is this point, if this point is V0, if we draw like this, so this is V0. So this is our we assume ions, and this is zero, this ions potential 0, this ion potential 0. In between two ions there is a potential barrier. So if we consider exists here Vx, and this is 0 potential, and this is A, and this is minus B. So this point is A plus B, and this point is minus A plus B. Minus A plus B. So for this square potential, the potential is V. Sorry, here I wrote VA, this should be Vx. By mistake I wrote this. So for this square potential valve, the condition is Vx equals to 0 when x is greater than 0 and less than A. When x is greater than 0 and less than A. Again, Vx equals to V naught, this point, when x is less than 0 and greater than minus B from here. So, for this square potential wall, which is developed by Croning-Penny model. So this is called Croning-Penny model. So if we consider here potential energy of this lattice, periodic lattice, at first we have to discuss another things of periodic lattice. In between these two lattices there is a spacing A. So this is minimum potential and there is maximum potential. Again this is minimum potential, again there is maximum potential, and this is going on. So the potential of in periodic lattice is Vx plus A equal to Va, which is varies. So in free electron gas model we learn only that things is potential energy is conserved and it is 0, but in periodic lattice we saw their potential energy is varying. So this is the one of the drawback of free electron gas model, and the accurate point is potential energy varies in periodic lattice in a crystal. Now we assume here a proper wave function psi k r equals to exponential I k dot r, and is a proper wave function and is close to very close to free electron gas. If we consider here one-dimensional lattice, so we can write wave function be like this: exponential I k dot x. But Bloch found in for periodic potential is to be modulated with another potential ux. Bloch found this. So this is known as Bloch function, and this is known as Bloch potential.